This is a schematic of the ME Hyperloop prototype built at the Indian Institute of Science. Operating at its limit, it hovers exactly 1.5 centimeters above an aluminum track, carrying a 1.2 kilogram load, driven by rotors spinning at 8,000 RPM. The engineering objective for this project is specific: to achieve magnetic levitation for a Hyperloop pod using an open-source, entirely passive track architecture. While this prototype operates on a 3-meter lab bench, the ultimate environment for this technology scales far beyond a single room. A full Hyperloop network requires hundreds of miles of depressurized steel tubes stretching between cities. Building that much infrastructure introduces an immense economic and structural hurdle. If the track itself requires complex wiring, power grids, and continuous active maintenance along every single mile, the cost becomes prohibitive. To make a Hyperloop network economically viable, the track must be cheap and simple as possible. The electromagnetic complexity has to be moved out of the track and into the pod itself, a requirement that forces engineers to use electrodynamic suspension. Traditional high-speed magnetic transit relies on electromagnetic suspension, or EMS. This image of a conventional Maglev system highlights the defining feature of EMS, an active electrified track directly beneath the carriage required to generate lift. Wiring hundreds of miles of Hyperloop tube with powered coils is both structurally complex and financially impossible for an open-source model. That is why the track for the IISc prototype contains zero wiring. It is built from simple, unpowered, passive sheet aluminum. Instead of a powered track, this system uses electrodynamic suspension. This diagram shows how it works. When a magnetic field moves rapidly across a conductive surface like aluminum, Faraday and Lenz's laws dictate that the motion induces changing currents, called eddy currents, inside the metal. Those eddy currents immediately generate their own opposing magnetic field. When that newly created field aligns against the moving magnet above it, they repel each other, physically pushing the magnet away from the aluminum. But this repulsive force must overcome gravity. In electrodynamic suspension systems, every gram of weight on the pod works against the lift generated by the magnetic interaction. To levitate over a purely passive track, the pod has to generate a massive localized change in magnetic flux to create enough opposing force, and it has to do so without adding heavy equipment that would ground the entire system. This diagram illustrates why standard magnets fail. In the alternating polarity arrangement, unlike poles touch, forming a symmetrical pattern. Half the magnetic flux points down, while 50% dissipates upward, providing zero left. To solve this, engineers implemented a Halbach array, a rotating pattern of neodymium magnets. This geometric rotation forces the field lines to combine on the bottom surface, producing a heavily concentrated field, while upward-facing lines cancel each other out. By focusing nearly all of the available magnetic energy downward, the Halbach array maximizes the lift force produced per gram of magnet mass. It extracts more levitation power from the same volume of material. However, inducing the necessary eddy currents in the aluminum track requires a constantly changing magnetic field. The pod cannot rely on forward linear motion to create this change if it needs to hover while stationary. The engineering solution is to translate the linear Halbach arrangement into a radial one. Here, the alternating north and south poles are mapped into a flat circular configuration. Wrapping the Halbach array into a spinning rotor allows the pod to generate a continuous, rapid change in magnetic flux over a single point on the track. The rotors do the moving, so the pod doesn't have to, solving the passive levitation paradox. To physically build this, the team 3D printed rotor discs out of a rigid material called Vero Black, precisely cutting out slots to firmly secure the neodymium magnets in the circular Halbach pattern. To induce enough current in the aluminum track to maintain a 1.5 centimeter levitation gap, the 4 rotors must spin at exactly 8,000 revolutions per minute when carrying no additional load. Operating at 8,000 RPM introduces a severe mechanical constraint. Slight imbalances generate high-frequency vibrations that rapidly travel through the frame and microfracture rigid materials. If the central chassis were to shatter during operation, it would violently scatter the neodymium magnets and jagged plastic across the room like shrapnel. To mitigate this risk, the IISc team opted against a brittle chassis, instead mounting the rotors to a square baseplate made of tan polypropylene sheet. Polypropylene offers a high strength-to-weight ratio, which keeps the pod under its 1.2 kilogram limit. Crucially, it is also highly ductile. This ductility means the chassis acts as a mechanical damper. It absorbs the extreme kinetic stress of the rotors, safely flexing and deforming under vibration rather than catastrophically snapping. With the frame secured, the next challenge is orchestration. How to simultaneously power and synchronize 4 separate rotors to that exact 8,000 RPM threshold. Examining the circuit schematic, the system begins with a 12-volt, 30-amp switch-mode power supply. During testing, this power supply remains tethered externally. Placing heavy batteries on the chassis would exceed the load limit. The current flows into the logic center, an 8-bit Arduino Nano microcontroller. To manually control the speed of the motors during the demonstration, engineers use a simple potentiometer, sending an analog input signal through this green wire. The Arduino translates that manual input into a pulse width modulation, or PWM, signal. PWM controls power by rapidly pulsating direct current. By varying the exact fraction of a second each pulse stays on, the system precisely throttles power. That pulsating signal is split and sent to 4 electronic speed controllers. Each ESC reads the incoming digital pulses and translates them into an alternating current, dynamically modulating the rotation speed of the connected motors. This real-time control loop is the nervous system of the prototype. Without exact PWM synchronization, the 4 motors spin at different rates. The magnetic field instantly destabilizes, and the pod violently crashes into the aluminum track. This diagram traces the orchestration of forces. A digital pulse from the microcontroller drives the brushless motor. The motor's rotational energy spins the Halbach array, bombarding the track with concentrated magnetic flux. The aluminum surface absorbs this flux, generating opposing vectors that push the entire assembly upward by 1.5 centimeters. Once that stable levitation gap is achieved, physical friction between the pod and the track is virtually eliminated. In this frictionless state, forward motion requires minimal energy. The IISC team easily propels the hovering pod down the acrylic guide channel using simply a blast of pressurized air from an external blower. The entire prototype is an exercise in energy conversion, turning digital electrical pulses into rotational kinetic energy, and then transforming that kinetic energy into a stable, repelling magnetic hover cushion over a completely unpowered surface. The ME Hyperloop prototype, built at the Indian Institute of Science, serves as a critical subscale proof of concept. It demonstrates that electrodynamic suspension on a passive track is physically achievable. Scaling this into a viable transit system introduces strict engineering hurdles. The first is untethering the power supply, engineering an onboard energy source dense enough to drive the rotors without crushing the pod's narrow weight budget. The second hurdle is control. The manual potentiometer must be replaced with automated onboard inertial sensors, capable of micro-adjusting PWM signals in real time. Finally, to prove the Hyperloop concept at its true scale, the system must leave the lab's open air and enter a fully depressurized environment. Mastering the 8,000 RPM Halbach array proves that levitation over cheap infrastructure is possible. Conquering the extreme aerodynamics of a near-vacuum steel tube will ultimately determine if the Hyperloop can become the 5th mode of global transport.